On June 22, 2025, the US officially deployed its most advanced bunker buster bombs, the GBU-57, for the first time. The targets were Iranian nuclear enrichment and research facilities buried deep underneath Natanz and Fordow. When the dust settled, the damage was immense, even if no one could reliably tell whether every facility was completely destroyed. But we've already analyzed the Operation Midnight Hammer in great detail in one of our previous videos titled B2 Operation Midnight Hammer Just Obliterated Iran. The partial success of the GBU-57 has also posed an increasingly important question for the US military-industrial complex. Can the US military truly reach and destroy any target in the world? Well, as it turns out, the GBU-57 is unlikely to remain the pinnacle of bunker bombing. So meet the new Iran killer bomb, the successor to the GBU-57 penetrator that promises some insane firepower. We're talking about the Next Generation Penetrator, or NGP, which represents the next revolutionary leap in bunker-busting technology. The NGP is expected to incorporate advanced capabilities that brings everything the GBU-57 previously did but better, at a longer range, and without a need for active guidance. When this monster is finally unleashed, no underground facility on Earth will be safe. Of course, the actual details and specifics of the NGP are classified and subject to change, but we can extrapolate some information based on limited news we have and how the current version operates. The first thing to do here is examine the existing capabilities, how the current systems work, and where the most likely options for upgrades lie. In truth, bunker buster bombs use a combination of simple physics and modern technology for devastating results. From a technological standpoint, what happens with a bunker buster is a kinetic breach followed by a delayed explosion. It might help to think of the GBU-57 as a massive, precision-guided drill bit filled with explosives. The GBU-57 weighs an incredible 30,000 pounds and stretches over 20 feet in length. Of those 30,000 pounds, only about 5,500 pounds are dedicated to the warhead or explosive material. The warhead itself is encased in a special high-performance steel alloy called Eglin steel, which accounts for most of the leftover mass. The steel alloy casing has multiple purposes, stemming from its large weight-to-surface ratio, which makes the bomb long but slim. First, dropping the bomb from a high altitude means it picks up speed quickly and has a high terminal velocity, both of which allow it to hit the ground with enough force to displace earth or concrete and dig itself in. The second part of the slim profile means that the bomb encounters less material as it plows through the ground. This reduces the stress on the explosive material inside and allows the bomb to dig deeper and longer than traditional explosive ordnance. Inside the casing lies a series of fuses whose alignment depends on how exactly the bomb is supposed to be operated. This can depend on the exact type of ordnance. The GBU-57 has a void-sensing fuse that is designed to trigger when it detects a sufficiently large open space, such as a room in an underground facility. This can be further combined with a delay element to allow the bomb to break deeper into the target before detonating for maximum impact. This fuse technology, aptly called Large Penetrator Smart Fuse, can ensure that the bomb detonates at exactly the right time, likely as a function of distance traveled when heavily decelerating, such as when digging through terrain. For the actual strike on Fordow, the US Chairman of the Joint Chiefs of Staff, General Dan Kane, noted that MOPs each had their fuse programmed bespokely for each weapon to achieve a particular effect inside the target, and that each of the 12 bombs had a unique desired impact angle, arrival, and final heading. Finally, there's the matter of how the bomb gets to its location. Traditionally, bombs are completely unguided pieces of ordnance, where they are dropped from a bomber, then follow a general parabolic trajectory to the ground, thanks to a combination of inertia and gravity. The main issue with the bomb's accuracy then becomes predicting the wind patterns or air pressure changes that can affect the bomb leaning to one side or another. For more modern devices, the addition of passive guidance systems like the Joint Direct Attack Munition, or JDAM, gives the bomb more aerodynamics and inertial guidance, coupled with common GPS. The added tail section and strakes lower the bomb's air resistance, and the GPS controls mean that specific fins can be adjusted to make the bomb change the flight path to achieve the optimal angle of descent or readjust course. In the GBU-57, however, the entire bomb is built with integrated inertial and GPS guidance from the start, reducing the risk of incompatibility. This allows the bomb to orient itself while nose down more effectively, but also gives it the ability to change the angle so it clears common surface obstacles or hits into reinforced structures inside hills. With the laser guidance integrated into the nose, the bomb can also achieve limited seeking capabilities. Also, thanks to the increased maneuverability and target guidance, the deploying bombers can drop the GBU-57 from higher altitudes or further distances to avoid being spotted by the enemy's anti-air defenses or radar, which drastically increase the operation's surprise factor and efficiency. The combination of all these factors resulted in the Iranian strikes being the first real showcase of the MOP's devastating effectiveness. Until then, there was no need to hit a target that was so heavily reinforced or dug in, and the MOP proved to be the only solution up to the task. However, the operation also revealed two major shortcomings of the system, which combined make it a more cumbersome solution going forward. First, the GBU-57 is a victim of its own massive size and weight. The US Air Force's current stealth bomber, the B-2 Spirit, can carry around 60,000 pounds of weapons in 2 bays, which is basically two 30,000-pound GBU-57B MOP bunker busters, the B in the name designation signaling the improved version with increased explosive yield. Another US bomber, the B-52 Stratofortress, can't fit the bomb despite technically having the payload capacity to do so, due to the fitting mechanism being specifically designed for the B-2. Even then, the stealth bombers needed to be retrofitted to be able to carry the bombs. This creates a massive strategic complication for the US Air Force, with only 19 B-2s in existence, as 2 of the original 21 were decommissioned after accidents. There's a very limited supply of bombers that can carry these massive weapons across the globe. Of course, that's partially counteracted by the estimates that only about 20 of the bombs were produced as of 2025, as well as the calculation that the complexity and strategic value of most scenarios would make the GBU-57s or other bunker busters only one of the payload weapons. With a limited number of aircraft that can be sent on the missions, the US always needs to think carefully about how many aircraft it assigns to each operation to reduce the risk of detection and subsequent losses. Which brings us to the second problem, the bomber itself. Although the B-2 has made headlines for its strategic use ever since its adoption in 1997, the 19 aircraft are starting to show their age. The US Air Force's answer to that has been to commission a replacement in the form of the B-21 Raider. The B-21 represents the future of American air power, designed to be produced in far greater numbers, with early estimates aiming to have it in service in the mid-2020s and plans for at least 100 aircraft versus only 21 B-2s ever built. Another estimate suggests that the B-21s will fully supplant B-52s by the 2040s, making it the only American bomber in use at the time, unless something changes drastically and a new design pops up. But the B-21, with all its improved stealth, cost-effectiveness and reduced size, which further reduces its visibility to radar and anti-stealth measures, has sacrificed a bit on payload capacity. As a result, the B-21 is expected to have somewhere around 40,000 pounds of payload limit. This allows it to lug only one GBU-57 bomb. For a mission like the one seen in Iran, the US would have needed to commit practically double the number of aircraft to achieve the same destructive capacity, not to mention that it would have a more limited supply of supplemental ordnances. The idea is that there will be plenty of B-21s to drop whatever payload needs to be deployed on any given target, regardless of the individual aircraft's smaller weapons payload. The Air Force realized that having more bombers with slightly reduced individual capacity could be far more effective than a tiny fleet of extremely capable but irreplaceable aircraft, which leads to why exactly the NGP is such a big deal. The NGP is envisioned as a more advanced version of the GBU-57 MOP, with a higher explosive yield in a smaller and lighter casing. It can also have an attached rocket booster for standoff strike capabilities, and possess the ability for precision strikes within a circular error probability, or CEP, of 7.2 feet, in both GPS-aided, degraded, and denied environments. Let that sink in for a moment. The next-generation Penetrator isn't just smaller and lighter, it's actually more accurate and more versatile than the weapon it's replacing. A February 2024 US Air Force contracting notice outlined the initial requirements: a penetrator warhead weighing no more than 22,000 pounds, capable of blast, fragmentation, and deep penetration effects. That's a dramatic weight reduction of over 8,000 pounds while maintaining devastating effectiveness. If the US military contractor chosen to create the bombs manages to eke out a bit more weight reduction, and the B-21 ends up having slightly higher payload capacity, there's a possibility that a single B-21 could carry 2 NGPs. In the worst-case scenario, if the NGP ends up being just above half of the B-21's payload, the bomber can still carry vital bombs that can be used in conjunction with it, but more on that a bit later. The combination of future-proofing the bomb's design to make it fit into a next-generation bomber will allow the NGP to be much more versatile in how or where it's used. But the real game-changer doesn't come from the reduced weight alone. There's also the addition of powered flight capability. It's been suggested that the NGP may be able to integrate rocket boosters for standoff strike capabilities. This is in stark contrast to existing GBU-57s, which don't have any propulsion mechanism, nor can they fit one due to their large size and weight. This solves another problem that the GBU-57 is believed to have: deployment range. Instead of requiring bombers to fly directly over heavily defended targets, the NGP can be launched from standoff distances, meaning that the aircraft might be able to stay out of the enemy's airspace while deploying the weapon and then turn around. This can dramatically reduce the risk to both aircraft and crew while expanding the weapon's tactical flexibility. For Iran, this added possibility already brings up significantly increased dangers. The new bombers could theoretically stick to airspaces far away from the Middle East. They would have the same standoff range as the AGM-181 Long-Range Standoff Weapon, or LRSO, which is around 1,500 miles, giving the US Air Force the ability to make precision strikes from the Indian Ocean or Greece. This would allow the US to launch attacks with negligible risk of detection and practically zero risk to the deploying aircraft, as it would be long gone by the time the bomb reaches Iran's airspace. The Air Force also requires terminal accuracy of CE-90 within 7.2 feet, meaning the weapon must strike within that distance of its intended point of impact 90% of the time, which is remarkable precision for such a large munition. For comparison, this level of accuracy surpasses standard GPS-aided JDAMs, whose accuracy can degrade to within 100 feet without GPS or 17 feet with it. It also outmatches Tomahawk ship-launched missiles, which have an error probability of 30 feet. The precision requirements become even more impressive when you consider the NGP's ability to operate in contested environments. The same contracting notice suggests that the US Air Force will consider novel, demonstrated or fielded guidance, navigation and control (GNC) technologies with viability for integration into a warhead guidance system that can achieve repeatable, high-accuracy performance in GPS-aided, degraded and/or denied environments. Let's translate a bit of this jargon. The NGP will supposedly be designed to work even when enemies are jamming GPS signals or using electronic warfare to disrupt navigation systems. For Iran, this might not matter as much, as its anti-air defenses are only limited to previous generation Russian designs, which have already been shown to be quite vulnerable to electronic countermeasures or even plain old lack of good parts. Where the added requirements might matter is beyond Iran. Think Russia or China, two countries that are likely to have and share cutting-edge electronic warfare capabilities. This is supported by the fact that Russia has been on the receiving end of Ukraine's electronic warfare systems, which have been indirectly and even sometimes directly supported by Western designs and donations. Meanwhile, China has been responsible for propping up Russia's drone industry and has risen as one of its few major importers of both materials and technology, despite practically worldwide sanctions. According to TWZ's interpretation of the contracting notice, the Air Force also seeks robust, embedded fusing technology to survive extreme impact forces and trigger at optimal depth. While the first is likely already covered by the capabilities present in the existing GBU-57, TWZ posits that there's a distinct improvement in the future weapon's ability to detect when it's breached through reinforced walls and entered the main section of the target. Beyond the aforementioned large penetrator smart fuse, this could indicate forays into floor-counting technology. Floor-counting fuses represent perhaps the most terrifying advancement in bunker-busting technology. Imagine a weapon that can literally count how many underground levels it's passed through, detect the layout of rooms and corridors, and then decide the optimal moment to detonate for maximum destruction. Sounds like something from science fiction. And even then, the existing fuse for the GBU-57 is likely specifically designed to work with the large casing inherent in the bomb. A smaller, leaner device like the NGP would likely need a different or modified fuse to correctly detect when it stopped moving, even before we add the potential of advanced detection. The combination of void detection, timed fuses, and floor counting will likely be critical for penetrating deeply buried, compartmentalized facilities where intelligence on layouts is limited or even non-existent. The US forces will only need to enter the precise coordinates the bomb needs to strike and insert the required angle at which to approach. The guidance system will launch the bomb semi-autonomously from the bomber, the inertial guidance will orient it for maximum ground penetrative power, and the adaptive fuse will determine the best possible time to detonate the explosives inside. This autonomous decision-making capability transforms the NGP from a simple bunker buster into an underground intelligence gathering and destruction system. It's not just destroying what it hits, it's learning about the target as it penetrates and adapting its detonation accordingly. If there's capacity for enough tech and distribution, the bomb might even be able to broadcast a scan of the facility moments before impact to American intelligence forces, providing an invaluable look into enemy operations and organizations. Finally, there's the matter of the weapon's actual destructive and piercing capability. While the details on the existing GBU-57 could only be gleaned from semi-reliable sources, reports indicate that the 60-foot piercing capability has been tested on 5,000 psi or 10,000 psi concrete. The psi here, or pounds per square inch, indicates the compressive strength of the concrete, or how much pressure it can withstand before it cracks or falls. A bunker buster uses the high-density alloy and a small nose circumference to channel its kinetic energy into a small section of the concrete reinforcement, which helps it surpass that resistance. However, Iran has been suggested to have developed concrete exceeding 30,000 psi, at least 3 times stronger than the rate-piercing capability of the GBU-57. In real-life applications, this can potentially cripple the bunker buster's capability to pierce through even the outermost layer of reinforcement, making it much less effective or destructive. And Iran's unlikely to be the only one to have that level of building reinforcement at the ready. Its long-term allies like Russia and China could have been watching the developments or even actively guiding them. Additionally, consider that China has started building a new People's Liberation Army command center in Beijing, which has been suggested to have underground bunkers and reinforced capabilities. This is one of the newest construction efforts by one of America's biggest geopolitical and military rivals, making it a potential prime target for long-range precision strikes by the same type of bomb used in Iran. If the GBU-57 proves to be less effective against newly developed designs, the NGP will literally be America's only other option. Of course, the NGP might not be the one-size-fits-all solution. The weapon is likely being designed to have increased penetrative rather than explosive capabilities. That could indicate that it will be used only to pierce into a bunker. Which brings us to another weapon, the AGM-181 LRSO. If the design trajectory for the NGP follows that of the AGM-181, we're looking at having two standoff long-range weapons that have autonomous guidance mechanisms. The AGM-181 will provide the sheer explosive yield, as it can fit an adjustable W-84 warhead with an explosive yield of up to 150 kilotons, between 1/3 and 10 times that of the bomb dropped on Hiroshima. However, the website 1945 suggests that it's possible that with 1,000 of the missiles being ordered by the US Air Force, they have not ruled out configuring the weapon to carry a more conventional explosive as well. Even more importantly, the AGM-181 is specifically developed to function for both the B-52 and B-21 bombers. This would allow the US Air Force to either solely deploy next-generation stealth bombers with a combination of NGP and AGM-181 payloads, or use B-52s to carry the bulk of the AGMs to the destination. The NGP will provide the penetrative capability, while the AGM will finish off the target, blasting it into pieces. Even with the B-52's reduced speed and stealth capabilities, the AGM only needs to get within some 1,500 miles to be successfully launched, and it doesn't need to fly entirely stealthy, as the first strike will already let the enemy know what's going on. Combination of the B-21 bombers with the NGP and AGM-181 underlines a potential solution to one of America's most pressing problems, and one that's plagued most procurement efforts: cost and scale. Beyond developing each weapon, the US needs to add the cost of researching and adapting existing platforms to carry them, or vice versa. The added budget challenges are a part of the reason why the B-2 was produced in such low numbers, as manufacturing costs skyrocketed to unimaginable proportions and forced the slashing of the order to a fifth of the original proposal. Furthermore, the B-2 is relatively inefficient, with a mission costing up to $150,000 per flight hour in fuel and operating costs. By unifying the development to fit on a single platform that already shows promise for mass production, the US Air Force could potentially field hundreds of NGPs, or at least have the capacity to order units on demand. This can reduce some of the bottlenecks inherent in current missions, such as only having 19 advanced bombers at its disposal or fewer than 20 bunker-busting bombs. And in the ongoing conflict with Iran, the US can receive more valuable intel to guide further development. Details on the GBU's effectiveness in Iran can guide the bunker-busting technology to meet and surpass future requirements, grounded in real-life operational intelligence rather than theoretical field testing. Through all of that, what we might end up seeing pop up in the next decade is a truly devastating weapon that no enemy can hide from. Thanks for watching, and if you want to know how the US developed its naval capabilities to match its air force, check out our video on hunter-killer submarines. And to stay up to date with news on global geopolitics and day-to-day missions of US and allied forces, subscribe to The Military Show. And thank you, as always, for watching.